Suppose we wanted we had two voltages V1 and V2. We had two independent voltage sources V1 and V2. We wanted to generate the difference between V1 and V2. How will we do this? Okay, so basically the insight is that we already know how to make so the gain from V2 to V out must be equal to minus 1. So, do we know how to make a gain amplifier with a gain minus 1? How do we do that? Okay. So, this is R and this is R and this is V2. So, the output is going to be V out is going to be minus V2. All right. So, okay, but to this we need to add V1. Okay. So, what do we think we should do? Okay. So, one idea is, all right, remember that this is, if we had a voltage source like this for V2, right, to add V1, to push all voltages up by V1, what do you think we can do? Where? No, if you add a voltage source in series, I mean, okay, one suggestion is, how about adding a voltage source like this in series? I mean, but that basically means that now you need to get minus V1, correct. So, if you want to push up all voltages with, if you have a circuit like this, right, I mean, let us say you have some circuit like this and this is ground, and you have some voltage here with respect to ground equal to VO. If you want to add 1 volt to all voltages to the output voltage, what can you do? You can change the ground voltage. So, if I put 1 volt here, the new output voltage will be VO plus 1 volt. So, now what do you think you know, so if you want to move the output voltage up by V1, what do you think we can do? You can connect V1 to so which is where all do we see the ground? So, if you did this, this will give you V1 minus V2. Does it make sense, folks? If you take the ground and push the ground up by a voltage, the ground node, and push the ground up by 1 volt by say some voltage V1, then the output voltage will also go up by V1. Does it make sense? Correct? Okay. But now the problem is that this V2 needs to be a floating voltage source. You need to have access to both terminals of V2, right. So, often that is not possible, correct. So, what is normally possible is that V2 is also, one terminal of V2 is grounded, you do not have access to that one terminal, so that you can push you do not have a voltage source with both terminals this thing. So, the only thing we can do is see if we put V1 here, what will happen to the what will happen to the output? What is the gain from V1 to the output? 2 times V1. But we want only one time V1. So, what do you think we can do? Yeah. So, basically the idea is if I put V1 here, I get 2 V1 at the output, correct. So, if I put half V1 here, then I will get V1 at the output. How do I get half V1 from V1? You basically take a resistive divider. So, this is basically V2 this is V1, okay, and this is V1 minus V2. Is that clear? So, this is the so called difference amplifier. Since the what do you call since it takes 2 voltages and generates the difference between these 2 voltages. Is that clear? Okay. So, now let us so basically with resistive circuit, I mean resistive circuits again, it's I mean if you want the op amp to behave like with with the difference between the 2 terminals to be 0, you must make sure that there is negative feedback around the op amp. Okay. So, now let us do an example where we do not know the sign. I will give you a circuit, we do not know the signs of the op amp. Let us try and figure out what the signs must be, so that there is negative feedback. So, here is an example. Okay. All right. So, we need to figure out whether what the signs of the op amp. So, the question is, this is let us call this A1, let us call this A2. What are the signs on the op amp for negative feedback operation? Okay, how will we figure it out? Well, no need for speculation. I am sure you have never seen this circuit before, right? Have you seen this before? Okay, do not worry about it, I have not seen it before either, right. But let us just use this as an example to figure out what the signs must be. Okay. So, I have never seen the circuit before, so I am going to break this, break the loop there. If I yank this voltage up, what happens to the output voltage? It goes down. Okay. And we do not know the signs, let us assume some arbitrary signs. Okay. I mean, let us assume that this is an assumption at this point. So, if this goes up, that goes down. If this goes down, what happens to this node? Must go down. If this goes down, and if these were the signs, what would the output, what would happen to that? It would go up, and therefore, it would be this choice of signs of the op amp would result in positive feedback. So, for negative feedback operation, what must we do? You must flip the signs, okay, and this should be plus and minus. Does that make sense? All right. So, now what is the output voltage? Pardon? By R1. Okay, there is no need for speculation. Please work it out. Huh? There is no RS in the picture. It's not clear. It's R3 actually. Okay, so it's all right. Huh? I got like 3 different answers. R4 by R1, R2 by R1, R4 by R3, minus R4 by R3. There are 4 resistors, you can pick 2 in 6 ways. What is the answer? Wait, how did we get the answer? What do? We know that both the op amps are in negative feedback. So, I mean, so there is no need for any speculation at all or guesswork. We know, we have checked that there is negative feedback. We basically, all that we need to do is simply apply the rules of for an ideal op amp. So, let us do that. So, what is that voltage? 0. What is this voltage? 0. Okay. So, what is this current? V in by R3. So, where will all that current flow? Through R4. So, what will that, what will be the voltage across R4? V in by R3 times R4. So, what is the output voltage? Minus R4 by R3 times V in. Okay. Does it make sense, folks? All right. So, so what is the voltage here? How will you find that? No, do it systematically. There is no need for speculation or guesswork. We know the voltage across R2. This is 0, this output voltage is minus R4 V by R3 times Vn. So, where will in which direction will current flow? Towards the output of the op amp. So, basically that will be the current. What will be that current? So, Vn times R4 by R3 times R2. Where will that current come from? It will come through R1. So, what will be the voltage here? The voltage drop across R1. The voltage drop across R1 is the current flowing through it multiplied by R1. The current flowing through it is already known. So, that is basically Vn times R4 by R3 divided by R2 multiplied by R. Does it make sense, folks? Easy peasy? Okay. And I mean, he basically said, okay, no, well, I don't need to do all that. I can look at it and tell you. That's also fine if you once you're familiar with all this. It's easy to look and this thing. So let me explain that. He says the output is minus R4 by R3 times Vn. The next step is to recognize that this is what kind of amplifier? Inverting amplifier with a gain minus R2 by R1. So, if the output of the amplifier is this, what should the input of the amplifier be? You divide the output by the gain. The gain is minus R2 by R1. So, when you divide the two, you basically the negative sign goes away, R2 comes to the denominator, R1 goes into the numerator. Does it make sense? Okay. All right. So, let us take another example. Okay. So, what are the signs on the op amp? The A1, the A2. What should the signs on the op amp be for negative feedback? All right. So, let us again there is no, let us not speculate, let us break the loop. Okay. So, and then I am going to yank this up. If I yank that up, what comment can I make about this voltage? It will increase. If that increases, what happens to this voltage? It will increase. Let me choose some arbitrary signs. Let us say this is plus and this is minus. So, what happens to the output of A1? Decrease. So, now is this negative feedback? Have the signs we have chosen, are they, will they ensure negative feedback or positive feedback? Negative feedback, correct? So, that basically gives you what you want. In fact, the signs are correct. That's what it means. What is V out by Vn? Yeah. So, well, again, there is no need to speculate. What is this voltage? Vn, simply because this drop is 0. So, this current is Vn by R1. This voltage drop is therefore Vn times R2 by R1. So, the output voltage is this voltage plus this drop, which is nothing but V in plus R2 by R1 times V in, which is therefore 1 plus R2 by R1 times V in. Does it make sense? Okay. So, and what comment can you make about this voltage? Yeah. So, well, there are two ways of doing this. You know, one way is to if you're very comfortable with this, then you can recognize that this is nothing but this is a non-inverting amplifier with a gain 1 plus R4 by R3. So, therefore, what must be the voltage here? V in times 1 plus R2 by R1 divided by 1 plus R4 by R3. Does it make sense? All right. So, I hope you got a hang of the analysis of ideal operational amplifier circuits, right, and most importantly, I mean, you know, so a common mistake to make is to apply the rules of the ideal op amp when there is no negative feedback. Okay. So, people forget the conditions that need to be valid for us to be able to apply this concept of virtual short at the input of the op amp. Okay. The key point to remember is that they can only be applied when there is negative feedback around the op amp. And it is very easy to check whether there is negative feedback around the op amp or not. You break the loop and then you basically figure out whether the feedback is negative or positive. So, let us take one final example. Let us take some numbers. Let us say this is R, this is 2R, this is R, this is 10R, let us say, sorry, let us R, let us say this is 10R. Now, the question is, A, first of all, what are the signs, how should the signs on the op amp be chosen, so that there is negative feedback around the op amp. So, how will we do this? We break the loop and apply a voltage, let us call that delta V. We set the input to 0, okay, all right. Okay. So, now what happens, what is this voltage now? Delta V by simply a potential divider, correct. What is this voltage? Delta V by 11. Okay. So, what happens when, so what is, let us assume some arbitrary signs, let us assume that this is minus and this is plus. Okay. So, so what is the difference voltage here? So, this voltage here is basically delta V times 1/3 minus 1/11th, which is positive or negative? I mean, this voltage is delta V times 1/3 minus 1/11. Is that positive or negative? Positive. So, if for this particular choice of signs, will the output be positive or negative? It will be negative. Does that make sense? Delta, I mean, the difference between the two input terminals of the op amp is positive. We assumed, just arbitrarily, we assumed minus and plus for the signs of the op amp, and the difference between the terminal on top and the terminal below is positive, and because we assumed the top terminal to be a negative sign, the output of the op amp will become negative. So, does this choice of signs result in positive feedback or negative feedback? Results in negative feedback. So, so these are the signs of the op amp. Okay. Now, for some other choices of resistor values, right. So, let us say I made this 2R and this R, and if I made this what do you call R and this 10R, what comment can we make about the signs now? Delta V goes there. What is this now? That's delta V by 11. What is this guy now? 2 delta V by 3. So, what is the difference between these two? Is delta V by 11 minus 2 by 3, which is negative. So, if this is negative and this is negative, what would the output of the op amp be? It would go up. So, what is the conclusion? This has got positive feedback. So, basically to make sure that there is negative feedback, we must interchange the signs. All right. So, what is the moral of the story? Every time you must check if there is negative feedback, right, even if the topology looks familiar, right. So, by just changing the values of the resistor, look what has happened. What was negative feedback earlier has become positive feedback. Is that clear? So, now once we have established the signs of the op amps for negative feedback operation, it is straightforward to find V out by V in. Now, what will we do? Well, the procedure is same old. So, what is this voltage? That's 2/3 V out, very good. So, what is so this is a virtual short. So, what is this voltage therefore? 2/3 V out. So, what is this current? V in minus 2/3 V out by R. That is the current there. So, what is the voltage drop there? The voltage drop there is basically 10 times V in minus 2/3 V out. So, what is the output voltage? So, V out therefore is this voltage V x minus 10 times V in minus 2/3 V out. okay, and Vx itself is 2/3 V out, so minus 10 V in plus 20/3 V out must be equal to V out. Does that make sense? So, what happens? V out times 1 minus 2/3 minus 20/3 must be equal to minus 10 times V in. So, V out by V in is minus 10 over minus 19/3, therefore, this is nothing but 30/90. Does it make sense? All right. So, so that basically these examples cover various situations where we have found the signs of the, we have learned how to find the signs on the op amp for negative feedback operation, and we have applied it to whole bunch of commonly used circuits, right. Some of the circuits we derived from scratch, namely the non-inverting amplifier, the transimpedance amplifier, and the inverting amplifier and the summing amplifier. And so, let's now start look. I mean, remember that the op amp, we said the model for the op amp was V out. It is a voltage controlled voltage source. We said is some k times, let us say some a times V a minus V b, where ideally a is infinite. In practice, commercial off the shelf op amps typically will have gains of 10⁻⁶ to 10⁻⁷, and but you know, this is basically this it turns out that this ideal model for the op amp is actually very simplistic. Nothing in the world is really ideal. So, there are a whole bunch of non-idealities in the op amp, okay. And you know, in the next class we will start looking at various common non-idealities that we have to be cognizant of, and see what effect they have on commonly used circuits. Does that make sense? Okay, we will stop here.